So in this video, I'm going to show you how to get 6 out of 6 on any rates of reaction 6 marker. If my audio is bad, forgive me, but it doesn't matter because after this, 6 marks every single time. Obviously, 0 to 6, that's why you're here. So in my opinion, there are 3 types of 6 markers. The first type are the rates table. So this is where multiple experiments are conducted to see whether or not a change in the concentration of a reactant actually affects the rate. It's just standard, and in my opinion, it's the easiest. The second one is a graph. I call it do-it-yourself because they're doing too much. Usually they give you the rate, but here they just want you to work it out. That's basically it. The third kind of question is everything. They'll just put any and every piece of information about rates they could. So here are the essentials that will get you 6 out of 6. And I'm going to go through each and every point. The last one I can't help you with, okay? You need to read that question yourself. So the first thing are rate concentration graphs. So 0 order, first order, second order. 0 order, you can see as we increase the concentration, the rate stays constant. So increase in concentration doesn't have an effect on the rate. So therefore 0 order. First order, as we increase the concentration, the rate increases by the same factor. So here you can see concentration does have an effect on rate. So therefore, it's first order. Second order is doing too much, going above and beyond, exponential, you get the point. Concentration time graph. So 0 order, you can see time on the X, concentration on the Y. As time increases, as time passes, obviously concentration is going to decrease because we've got a reaction going on. First order, you can see here, again with all of these graphs, the concentration is always decreasing, but it just gets a bit steeper each time. Okay, so our structure. Our structure is just going to help us write our answer in a way that's coherent for ourselves and the examiner. So the first thing that you want to do in any type of question is work out the order of reaction. But this kind of depends on which type of question you have. So if you have a rates table question, you need to compare the experiments. So basically just state which 2 experiments you're taking your data from. Then you need to say the order of reaction. This is just how you're going to phrase everything. And use WRT as an abbreviation. That just means with respect to. It just makes things a lot quicker. And then you say what factor the concentration of the reactant increases by. The square brackets, if you don't know already, it means concentration. Then you need to state what factor the rate increases by. And here's an example. So in experiments 1 and 2, order of reaction is first order with respect to the concentration of H+, as when the concentration of H+ doubles, the initial rate also doubles. If you got a DIY question, you need to work out the order of reaction using half-lives. If you don't know what a half-life is, you're going to get to know. If the half-lives are constant, so they're approximately around about the same value, it's first order. If half-lives are decreasing, it's 0 order. And if half-lives are increasing, it's second order. Okay? And remember, you're going to still use with respect to in this kind of answer as well. So here's an example. Order of reaction is first order with respect to the concentration of H+, as there are constant half-lives. If you got an everything question, so they might put a table in there, and if they do, just use what I said before. If they put a graph, use what I said before. If they put a rate concentration or concentration time graph, it is just one sentence, but you need to be careful in the way you word it. Here are the ways in which you will talk about the respective graphs in your answer to get those marks. So if it's a 0 order concentration time graph, you can just say constant gradient. If you wanted to do a bit too much, you can say concentration of reactant is inversely proportionate to time, just to help you make it make sense in your head, but saying constant gradient is more than enough. If it's first order, you would have to work out the half-life if they gave you a graph, and just say that constant half-lives indicate first order. If it's second order, just say the half-lives are increasing. Now rate concentration descriptions. So 0 order, as concentration increases, the rate remains constant. So you can literally just say change in concentration has no effect on the rate. You can say both of those bullet points, but the second bullet point is the main part. Same thing with first order. You can say rate is directly proportional to the concentration of the reactant, but that's a bit too wordy, and if you don't do maths like myself, I basically have no idea what that means. So the second bullet point, as y increases by x, so being the factor, so does the rate. So for example, as bromine increases by a factor of 4, so does the rate. That's basically you describing a first order reaction. Second order, again, rate is directly proportional to the square of concentration of reactant. That makes no sense. This is just a general like overriding statement. So if you're ever in a situation where you actually cannot work out the factor by which the rate or the concentration increases by, then just say that. If you can work it out, just do the same thing as it's written here for the first order reaction. So just say as concentration increases by 2, the rate increases by a factor of 4. The second part of our structure is to write down the overall rate equation. You literally just write it down. If you don't know what it looks like that. So rate equals to K, which is the rate constant, multiplied by the concentration of the reactants to their respective orders. So for example, you've got rate equals to K multiplied by H plus, the concentration of H plus to first order, multiplied by the concentration of I minus to second order. Anything that is 0 is not in the equation. Let me just point something out here. You don't really write the multiplication symbol over here. So you can just write a rate equals to K, and then concentration of H plus, and then concentration of I minus to the 2. The third thing you want to do in any sort of 6-mark question is to solve for K. That's basically the main part. So again, we're going to use the rate equation here. Rate equals to K multiplied by reactant, concentration of reactants to their respective orders. We're solving for K, so K needs to be the main character right now. So we rearranged it. K equals to rate divided by reactants to their respective orders. If you have a table kind of question, you need to use the concentration of reactants and the rate from the same experiment. So you can't just use the rate from experiment 2 and then use the concentrations of each reactant from experiment 1, because that's not the same experiment. You don't know whether or not those concentrations would actually give you that rate. Okay, if it's a DIY question, they usually expect you to do it yourself. So you need to find the rate by using the initial rate or drawing a tangent line at a specific point in time. So it's question dependent. So usually they ask you to work out the rate of reaction initially at 0, but sometimes they might ask you, hey, work out at 500, which in that case, you have to draw the tangent line at 500 seconds. And I have this equation right over here. It says K equals to ln2 over that little symbol over there, right? If you don't know what that means, that basically means half-life. You could use this equation to solve for K, but I would recommend you use the typical one, this one over here, because it's just standard. But I'll show you how to actually use this later on. If you got an everything kind of question, it depends on what information is given to you. So K might actually already be provided for you, so you might just have to rearrange the equation to find the rate, or you just have to prove that the rate equation provided in the question is the actual rate, by showing your workings out. The fourth thing that you want to do is to work out the units of K. So in order to work out the units for K, we need to know the units for everything else. So rate is equal to moles per decimeter cubed to the seconds, right? The concentration of reactants is moles per decimeter cubed. Again, that's our regular rate equation. That's our rate equation when we're going to solve for K. So here's how we're going to do it. Let's say we had an equation where rate was just equal to K and then the concentration of I minus. And then we rearranged it so it's rate over I minus basically, right, to equal to K. The whole premise of this is just we're cancelling stuff out. Okay, so you see here I've have the units of rate over the units of the reactants. You just want to cancel out any like terms. So in this case, the like terms are moles per decimeter cubed. So just cancel that out. What we're left with, seconds to the 1. What happens if I had 2 reactants underneath? So say if I had I minus and the concentration of H plus. So how would you work out the units if you had something like this? With rate over I minus over H plus, okay? Let me show you how you do that. Okay, so how we're going to do this is write out all the units. Okay, so I've written down my units. I know the handwriting is very messy. I have no idea how to use this pen. So on the top it says moles per decimeter cube per second. And you can see here we've got moles per decimeter cube, moles per decimeter cube. So that's the units for I minus, that's the units for H plus. Again, we just cancelled out like terms. So now we have seconds to the 1 over moles per decimeter cube. Does that look like a unit to you? No, it doesn't, right? So all you want to do, you want to move this bottom stuff over here, so moles per decimeter cubed, up here. And whilst you're doing this, you need to be mindful. You're basically inversing it, you're switching it up, right? So that means you need to switch up the actual powers that each thing is to. So before it was just moles, right? So now we have moles to the minus 1, decimeter cubed now, seconds to the 1. But what if it wasn't just first order, right? What if I had something that was second order What if I had multiple things that are second order? Well, in this case, this is what you would do. We're just gonna double it and give it to the next person, basically. So I've written it down here. It took me quite a while. But when I said we're gonna double it and give it to the next person, I don't actually mean that literally. When you do anything to the power of 2, you're squaring it. You're timesing something by itself. So if it was 2 to the power of 2, that's 2 times 2. So you apply the same thing here with the units. So if it was just like I minus just chilling being first order, of course you'll just write moles per decimeter cubed. But because it's second order, you're going to have to write it out twice. And you can see here, H plus is first order, so I've only written down moles per decimeter cubed here once. So, cancel out like terms, pull these two up, you do a little bit of like combining over here. So that'll give you moles to the minus 2, because we're inversing it, we're switching it up. Decimeters to the 6 now, because we've got 2 of them, and then again, seconds to the 1. Here's how to draw a tangent. So the reason why we're drawing a tangent in the first place is because the rate of reaction is not constant throughout. You can see here on the graph, the like curve of the graph, when it's steeper, that means the rate of reaction is like a bit faster. When it's less steep, it's going a bit slower. So a tangent is a straight line. And as you know, a straight line has a constant gradient. It's not like this line where it's switching up every 500 seconds. So you use change in y over change in x to work out m, which is the gradient. And the gradient gives you the rate of reaction at that specific point in time. So the gradient of a straight line, i.e. your tangent, is going to give you the rate of reaction at that specific time. So here you can see I've drawn a tangent line for the initial rate. What you want to do, you only want the line to touch that point once, okay? So you only want the line to touch 0, and then you just want it to get as close as you can to the rest of the curve. Same thing over here. So here I worked out the rate of reaction at 1,500 seconds. You can see that it only touches 1,500 seconds. The rest of the line, the rest of the tangent line doesn't touch the rest of the curve, but you need to get it as close to the curve as you can without crossing over the curve. Here's how to calculate our half-life now. So if you don't know what half-life is, it's the time it takes for the concentration of a reactant to half. So typically you want to work out 3 half-lives, and then you want to calculate the mean. This is just the way I was taught, and it got me the marks in the exam. If the half-lives are constant, not the same, so if they're like 800, 820, 790, that's constant, then it's first order. So there's actually 2 ways in which you can calculate the half-life. So the first way is actually using the concentration they've given you. So here we have 2.3 moles per decimeter cubed hydrogen peroxide. So we can work out 3 half-lives from that. So you can see here, I've got the first half-life, and then we need to do half of half. So you can see second half-life, third half-life. So you can see 2.3 is like over here, and then half of 2.3 is here. So that's our first half-life, and then second, third. But sometimes the graph they give you may be given to you in such a way that you're only able to work out 2 half-lives, which in that case, you can use a different concentration. So say, for example, 2 moles per decimeter cubed, I'll work out the half-lives of that. But you want to use the half-lives from that alongside the half-lives of the actual concentration they've given you. If I actually did use 2 moles per decimeter cubed, the half-life, half of 2 is 1. So here's our first half-life. That's how you draw a half-life, by the way. So you draw it up until the curve, and then when it reaches the curve, you go down. Second half-life, third half-life. Now here's a bit of cheating. This is what they don't tell you about A-level chemistry, because it's actually rinse and repeat. So you don't need to know any content whatsoever, guys. Of course I'm lying. You don't actually need to know everything in life. So a DIY question, you just assume first order. I've never seen it be work out the initial rate of this graph and it be 0 order or be second order. It's always basically first order. If the half-lives are looking dodgy, just lie, okay? Just lie. If you have 2 half-lives that are constant and then your third one is way out of range, that could literally mess up your whole value for the rate constant, okay? So just lie. So this is what I mean by lying. If it's so close to a line on the graph, just put it on there. You know how sometimes when you're drawing lines on a graph, they won't exactly land on the line. They'll land in between the square. They'll land, close to the line, and that just makes it difficult to calculate. So if it's close to a line on a graph, or if it's really close to being constant with your other half-lives, literally just lie and put it there. Because they're still going to give you consideration and marks for showing that you've worked it out on that graph, okay? And if your answer is right, and they've seen that you've drawn half-lives, you've basically got it right, like they don't care. Not sure whether your K is right. This is where you use the equation alongside the rate equation. So K equals to ln2 over the half-life. This is where you use it. Now the reason why I tell you not to use this equation, not to rely on it as your main source, It's because your half-lives are different to someone else's half-lives. That's not the point of the matter. The point is they're not going to be the same exact value. They must be to the same decimal point. So if both answers are 10 to the minus 3 for your value of k, you know that k is right. Because usually in the mark scheme, the value of k is within a range. Unless they're giving you a rates table, which in that case you have to get it right. If they give you any other type of question, the value of k is in a range. So if you see that your answers are similar in value, then you know your answer is right. Okay, so now I'm going to go through each question type, work it through, answer it. First one, rates table. You already know the first thing we're going to do is find the order of each individual reactant. And this is done by comparing experiments. So seeing whether or not a change in the concentration of a reactant actually changes the rate. And hopefully the questions that you get are easy. So we do this when a single reactant is changing. So you can see here in experiments 1 and 2, the concentration of carbon monoxide is not changing. It stays the same, yeah? But this, for NO, it changes. So that means any change in rate is going to only be due to the change in concentration of NO, not CO. So this lets us figure out the order of NO. So let's use experiments 1 and 2 first of all, because it's going to be a lot easier since we do not have to take into account the effect or the potential effect of CO on the rate. Okay, so experiments 1 and 2, you can see here that the concentration doubles. And with the initial rate, it actually quadruples. So since it's doing too much, we already know that it's second order. It's increasing by its square. The square of 2 is what? 4. So here's how you'd write down the answer. Experiments 1 and 2, I've stated which experiments I've gotten my data from. Second order with respect to the concentration of NO, as when the concentration of NO doubles, the initial rate quadruples. Simple. But now here's where it gets political, okay? It's going to get a bit difficult. Why? As we can see here, we use the change in the concentration of a reactant to see whether or not the initial rate changes. So obviously, we've just done that for NO, we need to do that for CO. But you can see that there is no point in time that NO takes a break. The concentration is always changing. So that means it's always having its effect, its second order effect on the rate. We have to take that into account when we're calculating the initial rate. If you guys have already done these kind of questions before, then I'll suggest you skip ahead a minute or two because I'm just going to explain the law behind all this. So, since we already know the order of NO, the first thing we want to do is we want to see what factor the concentration of NO increases by between two experiments, like we've just done before, except in these two experiments, the concentration of CO must also be changing. To determine whether or not a change in CO affects the rate, CO's got to change. So let's use experiments 2 and 3 for example. We can see here that it doubles. Since we know that this is second order, that means the rate over here is going to quadruple. Okay, so we apply this increase to the rate with its respective order, of course. So you can see here, I've done 7.4 times 10 to the minus 4 multiplied by 4, because second order, to get 2.96 times 10 to the minus 3. But there's something up, right? 2.96 times 10 to the minus 3 is not the same as 1.18 times 10 to the minus 2. It's not the same as our final value given in our table. That means there's still change to be done. That means CO is responsible for this change because NO hasn't completed the job. If it was the same, if by multiplying by 4, I got 1.18 times 10 to the minus 2, it means whatever NO has done is enough, okay? That means CO has no effect on the rate. But since we're not quite there yet, since we only have 2.96 times 10 to the minus 3, we know that CO is going to have an effect. So here's where we work out the order. If it isn't the same, so in this situation, so if it isn't, divide the larger rate of the two, so in this case 1.18 times 10 to the minus 2 with the new rate you've just calculated, to see the factor the rate needs to still increase by in order to get our final value, okay? So I know that it's very poorly worded, but let me just explain this for a second. So you can see here 2.96 times 10 to the minus 3, 1.18 times 10 to the minus 2. Some people fall into the trap of thinking that since 2 is bigger than 1, I'm going to do 2.96 times 10 to the minus 3 divided by 1.18 times 10 to the minus 2. But that's not right. You know, it's minus, okay? So the smaller this number is, the bigger it actually is. So if it was 10 to the minus 1, that's larger than 10 to the minus 2. Okay, so in order to work out the additional increase we still need, you'd obviously do 1.18 times 10 to the minus 2 divided by 2.96 times 10 to the minus 3. And as you can see here, we still need to increase the rate by a factor of 4 in order to get the actual value here for experiment 3. So calculate the factor, the reactant we are investigating. So as you can see here with this circle, the reactant we are investigating is carbon monoxide increases by. So between experiments 1 and 2, the concentration actually increases by 4. And what a coincidence, guys. We needed the initial rate to increase by a factor of 4 to get this, right? And guess what? We've increased it by 4 here. 4, 4, 4, 4. It's not a conspiracy, guys. It's first order. But that's honestly not what you would do in an exam. That was just doing too much. If you didn't know how to do it, that was that. But here's how you would actually write it. So you already see I've got our previous one here. But for CO, experiments 2 to 3 is first order with respect to the concentration of CO as the rate increases by a factor of 16, with the concentration of NO doubling and the concentration of CO quadrupling. Here's how I break it down personally in my mind. Like, I don't write this all down. So the overall factor that the rate is actually increasing by, so if we were to work out the increase with just these two things, this is actually a factor of times 16. We already know that this is times 2, and we already know that this is second order, so that's going to be times 4. What do I multiply 4 by to get 16? Times 4, so I need to times it by another 4. And our CO has provided that 4, so you already know that CO is first order. I just want to clarify that it's not always going to be that simple. So where I said that CO has actually provided that 4, that's not always the case. So for example, if CO was increasing by a factor of 2, but we still needed to increase the overall factor the rate increases by 4, we would know that that is then second order, because 2 to the power of 2 is 4. That's how that increase is still occurring. So sometimes the reactant isn't fulfilling its job, but then you deep it, it's actually second order. The rate equation. So rate equals to K NO to the power of 2, and then the concentration of CO just by itself. You could do it so there's a small 1 there to show first order, but don't do that because no one does that. Rate constant. So K equals to rate divided by the concentration of NO to the 2 multiplied by the concentration of carbon monoxide. That's just our rearranged rate equation. And then those are the values here. So I've used the values for experiment 1. Notice how I haven't switched anything up. So I haven't used, say, the concentration of NO in experiment 2. I haven't written down 5.5, okay? I've kept it simple. And then that's my answer for the rate constant, but it's not complete yet. We need the units of K. Okay, so I've written down what I need to write down for working out my units. Again, we're going to cancel out any like terms. That's all I can do. We're going to bring these two back to the top and we get an answer that looks like this. So those are the units for K. Just put that over there. And then that should get you 4 marks. It got me 4 marks. That's basically what you need to do. You can see here, look. And CO quadruple. You can see here that we need all this yap. Okay, here's a DIY question. Now, obviously the first thing we're going to work out are the orders, as I've said before. So in order to do this, we're going to draw our half-lives. So first, our first half-life is 900 seconds. Our second half-life is also 900 seconds. And our third half-life is 950 seconds. So they're round about the same. They're constant. Okay, so the mean half-life is 916.1, etc. Okay, you don't really need the mean half-life to say that it's constant half-lives. You just, well, me personally, I use that value in the other equation I showed you previously. So constant half-lives are present, therefore first order with respect to hydrogen peroxide. Okay, that's how simple the first mark is. Now we're going to do the rate equation. We already know it's first order with respect to hydrogen peroxide. So rate equals to rate constant multiplied by the concentration of hydrogen peroxide. Now we're going to work out the initial rate, because we need the initial rate to work out K constant. We need the initial rate to work out rate constant. So, change in Y over change in X. Here's my tangent line. I've used that coordinate. When you're working out initial rate, it's always easier to just use the coordinate at 0, like 0 on the X, because you don't want to spend your time just trying to pick out a coordinate that makes sense from the rest of the graph. Just use that. But if it's obviously on a different point on the curve, then do whatever you need to do. So those are my values. Here is me working out the rate of reaction, and I got 1.625 times 10 to the minus 3 for my rate. Now we need to work out rate constant. K equals to rate divided by the concentration of hydrogen peroxide. So that's equal to 1.625 times 10 to the minus 3 divided by 2.3. Because this is initial rate, so we're not using just any concentration. We need to use the concentration of hydrogen peroxide at 0 seconds. So K is 0. You can read the number, or 7.07 times 10 to the minus 4. I literally forgot to put this on the slides, even though I was talking about it so much beforehand. But this is working out the rate constant using the other equation. So you can see here that the answer that we get isn't exactly the same as our final answer. But the reason why I actually wouldn't really rely on this equation as your main source of working out K is because the value that you may get, so as you can see here, might be outside of the range. With this question, I don't know if it's within range. It's pretty close to our original value, but just a heads up. If you use the other equation, the rate equals to K multiplied by reactants to their respective orders, it's a lot better for you because the examiners can see you working out, see you rearranging. So if you do make a mistake, you're still able to pick up some points. But if you use this and nothing else, you have no sustenance. Some questions, they may ask you to put it in standard form. So you just want to make it a habit always putting it in standard form. Units of K. Now this is going to be easy because we just have moles per decimeter cubed to the second over moles per decimeter cube. So you know what? We just cancel that out. That's our unit. Did I get full marks? I did get full marks. You can see here that our value for K is matching, yeah? And you can see here with this other equation that the value of K is slightly different because that's because your half-life and your rate, they're not really like the same thing, okay? They're going to give you different answers. So use this equation to solidify the answer to this equation. Don't just use that by itself. If you're going to use it with the main one because this is what they want to see. They want to see your rate equation. They want to see everything, okay? So 6 out of 6 secured. Okay, so now I got my everything kind of question. And you already know the first thing we're working out are orders. So let's do this in order. Let's do this one first. So we've got concentration on the Y, time on the X. That's the concentration time graph. It's just a straight line. It's not getting any steeper. That's zero order. So zero order with respect to bromine. The second graph, let's look at it. Rate concentration graph. Okay. So we can see here the rate actually increases by the same factor that the concentration does. Why? Because it's a straight line. So that's first order. So first order with respect to the concentration of propanone, as rate is directly proportional to the concentration of the reactant. And now we need to work out the concentration of H+. So as you can see here, as the concentration of H+ doubles between experiments 1 and 2, the initial rate also doubles. So that's first order. Why? Because they're both increasing by the same factor. So first order with respect to the concentration of H+, as when the concentration of H+ doubles, so does the initial rate. Now we need to work out the rate equation. So here's our rate equation. You could write it like that, but why would you? No one does that. Rate constant. Here is our rearranged rate equation. So rate divided by the concentration of reactants to their respective orders. So now we're just plugging in values. If you don't know where I got this from this table over here. And we're not including bromine. Why? Because bromine is zero order. Okay, bromine does not make a feature in the rate equation because anything to the 0 is equal to 1. And anything multiplied by 1 is going to stay the same value anyway, so why are you going to put bromine in there? The rate constant is going to be 3.9 times 10 to the minus 5. But that's not complete yet. We obviously need our units of K. So I'm going to write down the units very quickly or very slowly because it's taking me quite a while. Okay, cool. I've written down the units of each thing over here. Just cancel that out. Let's bring that up. And it's going to be mole to the minus 1, decimeter to the 3, seconds to the 1. Remember, when we're bringing something up, we've got to reverse it. It's a new person. It's a new unit. And guess what? 6 out of 6 again. It's just standard. Look, they don't tell you to work out any units. And when it says explain how the reaction orders can be determined, don't want to see a PEE. They don't want to see a pretzel paragraph. They don't want you to actually talk, yeah? Let your working out do the talk. That's it. Subscribe only if you want to improve your grades.